Well, continuing on with some more problems for preparation for exam 2. I picked another one out of Miriam and Craig. They have a spring-mounted machine, has a mass of 24 kilograms, is there to vibrate harmonically in the vertical direction with an amplitude of 0.3 millimeters under the actual vertical force, which varies between FO and negative FO with a frequency of 4 hertz. If a static force of magnitude FO causes a deflection of 0.6 millimeters, calculate the equivalent spring constant for the springs which support the machine. All right, so this is a difficult one because of the nature of the way it's written. All right, so let's put this guy right into there. And so what you basically have to start with is we don't have a natural frequency. So, and we do know that we have a forcing frequency that's going to be this right here. And it's going to be the sine of omega ft. And omega ft can be found from taking 2 pi, multiplying 2 pi times f. Yes, I think that's right. So 2 pi times f, which is going to come out to 25.13 radians per second. So that's something I can get right away. So they say this FO right here. Got to be careful that this isn't FO. I think that's true. I'm trying to think. What they're basically saying here, all right, so if a static force, FO, causes deflection, right there, so we could say that we have like, let's call it XO, is going to be 0.6 millimeters. The idea being that you'll recall, I'm sorry, I'm jumping around here. So let's say we have FO divided by K. No, there's no damping here, so we have 1 minus R squared. So this is really sort of the equation that we're going to go to. And we could have a magnification factor is going to be equal to this right here. And FO over K. Right? But the amplitude is 0.3 millimeters, but you'll take a look at the denominator here, and they said the phrase that FO causes a deflection of this right here. So that would be FO divided by K would be a deflection right there. So what they just told us is that's the magnification factor. It was difficult to read and understand based on the words. That's what makes this problem kind of interesting. So anyway, that's going to be a 0.5 magnification factor. So what we can say is that 0.5 is equal to 1 over 1 minus R squared. And recall, though, that we had to be a little bit careful when it comes to our when it comes to solving for R here, because we really could have a different outcome, right? So we could actually, we could have that 1 minus R squared is equal to 2, right? So if we let it be positive, we want 1 minus R squared is equal to 2. We end up getting that negative R squared is going to be equal to 1. Right, which can't happen now. Then we'd have R squared is equal to negative 1, and R is equal to the square root of negative 1, and it can't happen. But instead, if we go to the negative route right here, right, and just ignore all that right there, we'd have a negative 1 plus R squared equals 3, excuse me, 2, I jumped ahead. Our r squared is equal to 3, so r is now equal to 1.732. And what I wrote next to mine was math thinking. All right, so don't just try to do the accepting type of thing. So this thing obviously could not happen as placed over here, but it can in this set of circumstances. All right, so one of the reasons why, if you take a look at the MF here, and this is, of course, this is R, and we go 1 and 1, we come up that way, and then we come down that way, right? So notice that we have an R, we have a magnification factor of 0.5, which is down there. So there's obviously, it has to be in the negative space over here and be over here. So that's why we found this right here. But we had to be doing math thinking to have that happen. And so now we can find out what the natural frequency is going to be, because we have R is equal to omega F over omega N. And now, so we could find omega N is going to be omega F divided by R, or we go 25.13 divided by 1.732. Did I do that wrong? 1 second. No, I should be right. So we end up with 14.51 radians per second. And I've been using red a long time. Let's go purple. So if that's the omega n, and we have omega n is equal to the square root of k over m, now we can find k is equal to m times omega n squared, and take a 24, and omega n is 14.51 squared, so k comes out to 5,053 newtons per meter. Oh, wait. The video is still going on. Done.